Uh, so, fe- so today we are dealing with damped harmonic oscillator. We have already discussed what are a simple harmonic motion, unharmonic oscillator, free oscillations, etc. So now it's damped harmonic oscillator. So what is meant by damping or damped harmonic oscillator? We know that if a simple oscillator, simple harmonic, simple pendulum is oscillating in a medium, when time passes on, the amplitude of its oscillation becomes fading, means it becomes small and small, or it comes to an end. That is, it is experiencing a frictional force offered by the viscosity of the air in which the medium is oscillating. So the system which is oscillating have to put an extra energy to overcome this frictional force of this air against the motion. So whenever it spends its energy to overcome this frictional force offered by the air, its energy decreases, or it's come to and rest after fading out its amplitude gradually. That is known as damping. So the damping force is the any force or any resistive force or dissipative force offered by the medium to the motion of the oscillating system, so that its amplitude decreasing gradually as time passing on. That motion is known as damping motion, and the oscillator which executes damped harmonic motions are known as damped harmonic oscillator. So, in case of damped harmonic oscillator, it experiences two forces. That is, the restoring force offered by, the restoring force, as we defined earlier, is proportional to the displacement. So, we can write restoring force is equal to minus Ex. The minus Ex, the reason of coming minus here. The restoring force is opposite to the displacement direction, so minus sign, and C is the proportionality constant. And if the velocity of the oscillating system is sufficiently small, the damping force experienced by the system is proportional to its velocity. So damping force proportional to velocity dx by dt, but opposite to the oscillations. Okay. Only for small velocity this is applicable, means it is proportional to the velocity. Hence the equation of motion can be written as force is equal to the damping factor, the damping force minus the this is the total sum of the damping force plus the restoring force. So we can write this equation like this. If we are taking the right side terms to the left side, the equation will become like this. And if we are substituting 2k is equal to gamma by m, this is again 1 by tau, where tau we can call it as relaxation time, and omega 0 is equal to square root of c by m. This equation will become like this: d square x by dt square plus 2k dx by dt plus omega 0 square x is equal to 0. So this equation represents the equation of damped harmonic oscillator. Instead of simple harmonic oscillator, an additional term appeared here. This is due to the damping factor, the damping force offered by the medium. I have already said T is the relaxation time and K is the damping constant. And now we have, if we are solving the equation of motion of damped harmonic oscillator, that is equation 1, we will get the solution of that equation, which will be the displacement, because it is a second order differential equation in X. You have already studied the solutions or solving the second order differential equations in your mathematics classes. So the possible solutions of this equation is x is equal to a e raised to alpha t, and if we differentiate this equation with respect to t, we will get alpha a raised to alpha t, and if we differentiate again, we will get d square x by dt square like this. Put these equations back into equation 1, we will get the second differential equation of motion of damped harmonic oscillator like this. Now a raised to alpha t is common in every term, so it can be omitted, so it can be cancelled, so we will get a quadratic equation like this. So any quadratic equation can be solved by the equation minus b plus or minus square root of b square minus 4ac by 2a formula. If we are using that equation, we will get the solution, the value of alpha as minus 2k plus or minus square root of k square minus omega 0 square. And the solution of equation 1 will get by putting this alpha back into this expression. Now we have find out the value of alpha, and putting back this into this equation, we will get x. Now x is a1 e raised to minus k plus square root of k square minus omega 0 square into t, and minus two values plus or minus. Here we have two values plus or minus two values for displacement. It's quite obvious because it is second order differential equation too, so it will have two solutions. The most general solution therefore will be the combination of these two, that is x a1 e raised to minus k plus square root of k square minus omega square t plus a2, and the second solution. And what we are doing in the next step is we are taking the exponential factor e raised to minus kt, the first term. From both the terms, we are taking e raised to minus kt outside, so that this equation will become like this. Here a1 and a2 are constants depending upon the initial conditions of motion. Depending on the relative values of k and omega 0, the quantity k square minus omega 0 square is imaginary, real or 0, because here the term is square root of k square minus omega square. So depending on the values of k square and omega square means whether k is greater than omega or less than omega or equal to omega, and depending on these conditions, its value will become different. So we are going to discuss the three different cases of this. Here k is the damping constant, omega 0 is the angular frequency, we know. So three different cases are: the case 1, if k is less than omega 0, then square root of k square minus omega square is an imaginary number. That case is known as underdamped case, and we will discuss it here. If k is greater than omega 0, it will be a real number, so it's an overdamped case. And if k is equal to 0, it's a critically damped case. So we are going in detail of these three cases. So first is underdamped case. Here if damping is so low that k less than omega 0, that is damping factor k is very much less than the omega 0, then what will happen? K square minus omega 0 square will become imaginary. Here we are taking the minus sign outside, so that it will become omega 0 square minus k square. So minus 1 is square root of minus 1 is I, it's an imaginary number, and square root of omega 0 square minus k square is omega, that is we are substituting this as omega. So we will get the square root as I omega. Now x is equal to so that x is equal to e to the power minus kt a1 e raised to I omega t plus a2 e raised to minus omega t, because we have substituted this term as I omega, so that our equation becomes like this. Now what we are doing is expanding this e raised to I omega t and e raised to minus I omega t. E raised to I omega t is cos omega t plus I sin omega t, and e raised to minus I omega t is cos omega t minus I sin omega t. And what we are doing is we are taking e to the power minus kt outside the bracket and combining the a1 plus combining the cos omega t term and sin omega t term together, so that it will become a1 plus a2 cos omega t plus I into a1 minus a2 sin omega t. As x is the value of displacement, so it will be a real quantity. Real quantity a1 plus a2 and I a1 minus a2 must be a real quantity. Since x is real, we are expecting a1 plus a2 and I into a1 minus a2 real quantities, otherwise it won't happen. Clearly a1 and a2 are complex quantities. We know from this equation, it's clear from this equation. So what we are doing is, if a1 plus a2 is equal to a0 sin phi, but we are making a substitution like this: a1 plus a2 is a0 sin phi and I a1 minus a2 is a0 cos phi. Then what will become? Here this term is a0 sin phi and this together as a0 cos phi. So a0 is common, a0 can be taken outside, and the remaining terms like sin phi cos omega t plus cos phi sin omega t, which is like sin a cos b plus cos a sin b, which is sin a plus b, so that the solution will become x is equal to a0 e to the power minus kt. Here we can use capital A0. I have used in the previous equation capital A0. It's my mistake. Whether it is capital A0 or small a0, it's not a problem. And the meaning is it's the amplitude of oscillation sin omega t plus phi. This equation represents damped harmonic motion. So this is the displacement of the damped harmonic motion. This motion is oscillatory or ballistic. So this equation is known as oscillatory. So you can find an exponential term here and a sinusoidal function here. Also due to this function it will be oscillatory. It's quite obvious. So this motion is oscillatory. And the period of this equation can be find out using t is equal to 2 pi by omega equation, where omega is square root of omega 0 square minus k square. Thus the effect of damping is to increase the periodic time. Periodic time, that is the term here is square root of omega square minus k square, which is less than omega, so that the period so the period will be large. Means the denominator is a small quantity compared to omega, so period will be large. So the effect of damping is to increase the periodic time. If k is equal to 0, that is not damping, then t will become 2 pi by omega 0. But in actual case, the effect of damping but in actual case, the effect of damping on periodic time is usually negligible, except few extreme cases. The amplitude of the oscillatory motion is given by here amplitude is given by this term. Amplitude is given by this term. This is a0 raised to minus kt. Where we have made a substitution. We have already made a substitution. 2k is equal to 1 by 2. If you are using that here, it will become a0 to the power minus t by 2 tau, where a0 is the amplitude in the absence. So this term alone represents the amplitude in the absence of damping, and in the presence of damping the amplitude decreases exponentially with time. That is this term represents, because the amplitude is decreasing as the time passing on in the case of damped harmonic oscillator. So the in the damped harmonic oscillator, the amplitude is this, and this term represents if there is no damping. So its oscillatory motion can be represented in a graph like this. Then the x-axis it is time and y-axis it is displacement. How this graph comes? As the maximum value of sine omega t plus 5 is alternately plus 1 and minus 1. We know the sine function values can have maximum value as plus or minus 1. So obviously the time displacement curve of the vibrating body lies entirely between this curve. So the maximum value will lie between plus 1 and minus 1. So this oscillatory motion will be between plus 1 and minus 1. It's quite obvious since the sine function can can have up and down values maximum as plus and minus 1. And we know the amplitude of this damped motion is a0 e to the power minus t by 2 tau. And then in the negative side it is minus a0 to the power minus t by 2 tau, because if the system oscillating, the amplitude will vary maximum minimum maximum minimum, and it will oscillate in between the sine envelope and its maximum amplitude plus and minus of these values. It is represented by this dotted curve. Okay, so it can't go beyond this limit, plus 1 and minus 1 limit. And you can see from this graph that this amplitude is decreasing as time passing on. This is due to this factor, because there is an exponential term e to the power minus t. So as t is increasing, this factor is decreasing, so this will become, amplitude will become less and less. So that how this graph up comes here. The time interval between the successive maxima displacement, that is amplitudes of left and right side, is t by 2. Hence which means the time interval between the successive maximum displacement. Successive maximum displacement means this or this. These are maxima. These are maximas on the positive side and these are maximas on the negative sides. So what we mean is the time interval between successive maximum displacement, that is amplitudes of left and right sides, is t by 2. So this is t. So the time interval between this is t by 2. That's what we mean. Hence if an and an plus 1 are the successive amplitudes, then an is equal to a0 e to the power minus kt, and an plus 1 is equal to a to the power minus t plus t by 2. So if this is the amplitude first, suppose this is the first amplitude position, or this is the nth amplitude position. So we can represent it equation like this, and the next amplitude positions on the other side is a n plus 1. It is after a period of t by 2. The period will complete after this time interval, or after the next maximum amplitude position. So this is at a time t, this is time t by 2. So that we can write an and an plus 1 like this, and if we are dividing both this, we will get e to the power minus kt by like this, and which is equal to e to the power kt by 2, which we can represent as d, a constant for motion. Where d, here d is called the decrement, indicating for the reduction in amplitude. So this term d, e to the power kt by 2, represents the decrement in amplitude. So this how much quantity is decreasing in amplitude in every interval. So if you are taking natural logarithm, L and D will become kt by 2, which is equal to lambda, where lambda represents the logarithmic decrement and is equal to the ratio of the natural logarithm of ratio of two successive amplitudes of vibration, that is here to successive amplitude of vibration. Now we are going to discuss the second case, over damped case. If the damping is so high, k is very much greater than omega 0. Then k square root of k square minus omega square, same, beta is a real quantity. Okay, that is we are substituting it as beta, and then from our original equation 3, we can substitute these values here, so that this equation will become like this: e to the power minus k square root of k square minus omega square now become beta. We have substituted the beta value for that, so that this equation will be like this: as k is greater than beta, both quantities of RHS decreases. Since k is greater than beta value, this term will be a positive quantity or real quantity, and the exponential term is minus of this quantity, so it will exponentially decreasing. Both the terms will be exponentially decreasing with time, and the motion is non-oscillatory. Such a motion is called deadbeat or aperiodic, and its main application is in deadbeat galvanometer. So now we could see that the oscillation is deadbeat or aperiodic, non-oscillatory. Okay, now the third case is critically damped. If k is equal to omega 0, then x is equal to a1 plus a2 e to the power minus kt. Because other terms, k is equal to omega 0, square root of k square minus omega square will become 0, so that x is equal to a1 plus a2 e to the power minus kt. So this we can written as c e to the power minus kt, where c is a1 plus a2. In this equation, there is only one constant, hence it does not provide us the solution of differential equation 1 of second order. So our original equation is a second order differential equation. If we are substituting like this, we will get only one solution, so which does not satisfy our original differential equation. So what we are doing is, now we are supposing square root of k square minus omega 0 square as h instead of 0. That is that is k equal to c. When k is equal to 0, it will be 0, but we are not taking like this. We are what we are doing is, it's like k square approximately equal to omega 0 0. K is approximately equal to omega 0, so that square root of k square minus omega square is equal to h, a very small quantity, that is a slight difference. Okay, so we are substituting this in our equation, and the equation of displacement, it will become like this. In the exponential term, the square root of k square minus omega square will become h e to the power minus kt is keeping outside the bracket. And what we are doing is expanding these exponential terms using the series expansion. So it will exponential e to the power, the expansion of it, the series e to the power x is 1 plus x plus x square by 2 factorial plus etc, and similar to e to the power minus x, and this equation will become like this. Neglecting the small terms containing h square and higher powers of h, we get, that is, h is a very small quantity. So h square h cube term can be omitted, and we are keeping the first order term only, so that this equation will become x is equal to the power minus kt a1 plus a2 plus h into a1 minus a2 into t. Only the term containing h we are keeping, other terms are omitted. So we are substituting a1 plus a2 as b and h into a1 minus a2 as q, so that this equation will become like this. Also from x dx by dt, this equation we can write it, that is differentiating this equation with respect to t, we can write it is like this, differentiating with respect to t. If initially at t is equal to 0, the displacement of the particle is x is equal to x0. So we are putting the initial conditions here at a time t is equal to 0, x is equal to x0, and the velocity is v0. So these are the initial conditions. T is equal to 0, x is equal to x0, and v is equal to v0. If we are putting these conditions, then x0 is equal to x0. We are substituting it here at t is equal to 0. T is equal to 0 means this term 1, this term 0, so that x will become p. And v0 is, this is the equation of velocity. Dx by dt is the velocity. Substituting the condition of t is equal to 0 here, so we will get v0 is equal to q minus kp. Q minus kp means the and t is equal to 0, this term will go, this term will be 1, and this term will be 1, so that we will be, in the first term q remains, and in the second term minus k into p. That's how this comes. And here p is x0, x0 is equal to p, so we can substitute x0 here instead of p, so that v0 will become q minus k x0, or q0, q is equal to v0 plus k x0. Now x, the value of x becomes x0 plus v0 plus kx0 into t e to the power minus e into kt. That is, we are substituting the value of p and q in this equation, putting back this in this equation. So we will get x is equal to like this equation. This equation represents that initially, so if you note this equation, you can see two terms containing t, containing the term t, containing the factor t. This is linear, this is exponential. So this equation represents that initially the displacement increases due to the factor this, because this is a linear term. So as time increases, the which means x is proportional to t. So as time increases, the displacement or its amplitude increases. But as the time elapses, as the time is going pass on, the exponential term becomes relatively more important, because that term is e to the power minus kt. As time becomes larger and larger, that is, as time passing on, that term will become dominating, so that dominating, and it is an exponential quantity with a minus sign, so that means decrease in that quantity. So as time passing on, the second term or the exponential term will become dominant, and the amplitude will starts decreasing. And the second represent becomes relatively more important, and the displacement returns continuously from the maximum value to 0, and the oscillatory motion does not just occur. Such a motion is called critically damped, or just a periodic motion, which means in this case the amplitude is increasing in the initial stage, but as time passing on, the second term dominates, and it comes to an end, or its amplitude becomes 0 from maximum. So it's known as aperiodic or damped case. So these are the three cases these are the three cases of damped harmonic motions. So we have seen what is damped harmonic motion and damped harmonic oscillator. Okay.